Typically, when I get a CAD design from a client, it includes a lot of details like bolts, welds at these locations here, here, and at this point, this location here. If I'm uh, analyzing an existing structure, I will have all these details in my model, and then I'm going to do what is known as a detailed design evaluation. But if I'm coming up with a new structural concept, I, uh, I, I will basically start with a simplified model. I don't need these details because I don't even know. This is not an existing design. I don't know the forces involved. I actually have to find these forces and loads. So I can start with a sketch. I can do some hand calculations, and and that is highly recommended. I mean, before we get into finite element analysis, it's important that we have some sort of an idea of what the structure can bear. What is the magnitude of load it can take, and a lot of this can be done using simple uh, formulas from solid mechanics, like the bending and flexure formula, the torsion formula, the uh, we can even evaluate buckling loads, and and using that we can come up with a rough size or geometry of the structure, and then we can dive into finite element analysis. We can also use hand calculations to basically validate our finite element analysis. So in this case, you can see a simple design. This is not an existing or pre-existing physical structure. I just made it up to show how design is done, and the purpose of this video is to basically show how we can go about doing an analysis from scratch in ANSYS. Um, ANSYS is one of many finite element analysis softwares. I'm not uh, you know this is one of the softwares that I use. There are other softwares. I'm not you know marketing ANSYS here. It's just that I'm going to show what I have. Other FE packages work equally as well. So so yeah. So the purpose of this video is to essentially show how this analysis is done, and the different levels of fidelity that we can go into. So this one is a solid model. I have created two other embodiments of this design. So I'm going to convert uh, this one in the middle into a shell model, and this one is going to be a combination of beam and shell. So as we go from this model to this model, the analysis and the modeling is going to be of lower fidelity. So that's the aim here. So let's begin with suppressing this. I'm going to put this into its own component. Yeah, so we can put each of these components into its own folder, or we can create like a single component with multiple subcomponents, if you will. The way SpaceClaim works is that this is the top level assembly, and then we have components. Ideally, every component should be in its own sort of folder, like this one, like shown here. But we can also uh, just combine a bunch of components into a single component and call it a single component. So let me do that. So I'm going to call this one as solid, because this is all solid uh, parts, and I'm going to hide this one. So I'm going to then use the mid surfacing tool to convert the solid um, this solid geometry into shells and beams. So here we go. So I'm picking mid surfacing here. Click once, click twice, click once, click twice. So you keep going like this. Okay, I can convert this also into a surface. So here we go. So now these are all um, shell elements, shell components, and we will be meshing this using shell elements. Similarly, I can extract these members into beams. So I'm going to go here, extract, click this one here, this one like this. So now I can move these into this one into, oh, let me just back up. Move this into a separate component, and I'm going to call it shell, and hide this one. This one, including the beams, can be moved into another component, and I'm going to call it beam. Actually, it's beam and shell. Okay, so we have three different uh, geometries. This one is a solid model. This is how it came in Space Claim. The middle one is a shell model, and this one here is a combination of shell and beam or beams. So next step is to prepare it for Workbench. And what I'm going to do is, first of all, close solid model, and yeah, we can share the nodes at these locations. So I'm going to go at these locations and basically share the nodes when we mesh it. So, and it's picking this point also. So we can simply click yes. The purple here means that this is now mesh connected. So when we bring it into ANSYS mechanical, it's going to be meshed as one continuous geometry. So there's going to be node sharing at these locations. Now at this point, I can, let me just hide this for a second. So there's this option of extend, where I can extend these beams to merge into, you know, uh, the adjacent or nearby beams if I have a maximum distance tolerance of 10 millimeters. So I'm going to do that. So this is where we merge it. Another thing I want to do is I will if you see it from the side view, you can see this beam passing through the plate. I can delete this like so, and let's see. I I can again go into share and press share. So now we have these two uh, members merged into the surface. So these are all connected. This one has a gap. Uh, so the idea here is to follow this 3D solid model. This beam is not in line with this beam, right? So this member is sitting on top and it's probably bolted or adhesively bonded here. I'm trying to model the same effect. So I have this member, separated. And if you want to see it, let me show you this. The beam is going to, it's not going to show you now because it's being extracted and for some reason it's not showing me the 3D version of this beam. But my point is, this is going to be modeled exactly like this one. There's going to be an offset. This beam is not going to be in line with this beam. There's going to be a gap here, and that's okay. So let me just open up all these models and check one more time. So another thing we can do before we bring it into ANSYS Mechanical is to create name selections so that we can apply boundary conditions rapidly in ANSYS. So let me do that. So I'm going to pick this face here, and so I'm basically going from structure to groups. I'm picking up this point, this surface here for the solid model, and create name selection. I'm going to call it solid force face. So the idea is to apply a force along this direction, along the direction of this member, on all these models, and then compare the results. So the force is going to be in this direction, and then this structure is going to be connected to a support structure, which is not shown via these bolts or these through these holes here. So that's one name selection. Then I'm going to pick this edge and create another name selection. Call it shell force face. Now for the beam model, I just have to pick this endpoint here, create name selection, beam force vertex. So likewise, I can create name selections for these bolt holes. So let's do that. So for this, I can use my selection. I can, we need to come into this selection tab, pick this hole, select all holes of this diameter on this member. I mean, I'm not picking holes in any other plate here. I'm just picking holes in this one. If I select all bodies, then it's going to search for all bodies with the same diameter. So this is what I need. So I can come here and create another name selection. Call it solid holes. Likewise, repeat this here. Shell holes. plate holes. Okay, so that is done. I'm just going to check if there's something else that we can do here before I bring it into. Okay, so since we moved these models into different components here in the structure, we can delete empty components. So a space claim preserves the original geometry here. So if you want to look into what the original geometry looked like, we can just click these suppressed components here. So these are the ones that we are going to be bringing in into mechanical. Okay, so here we are in ANSYS mechanical. I have these three identical subassemblies. The first thing I'm going to do is to organize my geometry into separate folders. So this is going to be solid. Group this one into shells. And this is going to be beam, shell. So in materials we can see structure of steel. I want to use aluminum alloy for this analysis, so I can just add that, and like so. So you can see these properties here. So I can just go around picking all these components. Assign aluminum alloy. Likewise here. Just to be sure, we can switch this, click on geometry, come down here and pick material, just to be sure that everything is converted into material that we need. If we have multiple materials, then this is actually really helpful to see if we have assigned the materials correctly. So I would highly recommend doing this. Another thing I want to do is to assign the correct element orientation, and you will understand this when we go into results. So the basic reason is, we have a global coordinate system. These members are in different orientation. So in order to see results in a particular direction, let's say x-axis, I can use my solution coordinate system or the element coordinate system, and so that's what I'm trying to do here. So I'm going to go here, pick this surface, pick this geometry first of all, and let's say this is the Z normal surface, and then pick this edge for the x-axis. So what I want is, so let me take a step back. For the beam elements, the x-axis is always along the beam axis, and then we have the z and y-axes uh, in the plane of the cross section of the beam. So I want to orient all these elements in the solid model and the shell model in the same orientation as the beam element coordinate system. So that's what I'm doing here, and as you can see. So what I care about is basically the the x-axis. I mean, this should be aligned for each one of these elements in along along the axis of the beam. So we can do the same for the rest of these elements here, members here. So let me just duplicate this. That face here, this edge. See, this is the most important item here. So here I'm actually selecting along which axis I want my elements to be oriented. So this is the x-axis. And generate these elements here. So just making sure we have the x-axis along the axis of these members. So So just double checking if my orientations are correct. So this is the x-axis here. This one. Okay, seems okay to me. The beams are already, as I said, I mean the elements are already oriented in this fashion. So the local coordinate system has the x along the beam axis, and then the z and y axes are in the plane of the cross section. So that takes care of the material and element orientation. Then we can come down here. Okay, let's do contacts. So these contacts were automatically generated. You can turn it off here if you don't want this to happen again and again. It can be really annoying at times. Whenever you update your geometry, it generates a fresh set of contacts which you don't need. So I usually turn it off. So that's the contact we wanted. That's good. That's okay. Okay, so I can group this into solid. For the shell model, we do want this connection here. But if you recall, these connections here, here, and at this point were merged. So there's a shared topology here. So when we go into meshing, it's going to generate the mesh which is conformal. So the nodes are going to be shared between this member, for example, and this member at this location. So the only contact we need for the shell model is this one right here. I can group this one into shell. So likewise for the beam elements, we have a conformal mesh here and at this location, but not this one here. So I need a joint to connect this node to this node. So let me do that. So I'm picking the vertex selection here. Pick this one, and then this one here. So we can now come into the mesh section. So as you can see, this node is shared between the plate here and the beam. We cannot share nodes between uh, a beam element and a solid element because the beam element has 6 degrees of freedom and a solid element has 3 translation degrees of freedom. So you know there are ways of connecting them. I'm not going to go into that, but just so you know, we can share nodes between a shell and a beam element without a problem. So let's see here. Looks like these nodes are also shared here. Okay, so let's start with the solid model here. So I can do insert, sizing. So this is a 2 by 2 inch by I think 1/8 inch aluminum tube or section. So I'm going to go with a 1/4 inch element size. Let's see how it turns out. So I can start with that. Actually, I can select these two also. And this plate is a 1/4 inch thick. So since this model is going to be meshed with solid elements, I want at least 2 elements through the thickness. Before, yeah, so we can just add another. We can just add this face mesh here. Before I do that, I need to hide this. So I can do face meshing here. And on this cross section here. And since I want um, 2 divisions through the thickness, I can set it to 2. Generate mesh. Yeah, so you can see the mesh is now showing 2 divisions through the thickness. Let me check this one here as well. Okay, so that works. I can also do 2 elements through the thickness on this plate. To do that, I can use the method, pick this plate, select sweep, and all quad. Number of divisions is 2. Generate mesh. So once I mesh this component here or subassembly here, I can just to organize better, I can just group this into a separate folder. So I can call it solid. I can repeat the same a similar process for the shell model. Here I don't have to worry about number of elements through the thickness because this is a shell model. So all we need to do is set the size, generate mesh. Put this into its own group, call it shell. Sizing. So I'm now setting the size for the beam model. For the beams, I'm going to pick the edge option. And generate mesh. As you can see here, the mesh, these nodes are shared between this body here and this body here. Likewise, between the plate, attachment plate here and this member here. as you can see. So I can put this into its own group, call it beam and shell. Okay, so we have a bunch of name selections that we created in space claim. So we can just go down and apply boundary conditions. So as you can imagine, this plate is going to be connected via these bolts, and so that's what I'm going to pick for my fixed support. So come down here, pick name selection. This is a solid geometry, so I'm going to pick solid holes. Duplicate shell, duplicate let's check this again. This has to be holes here. Okay, so these are my fixed support. If I want, I can just group this into its own folder, fixed supports. Insert. I'm now going to apply a force of, I would say, 10 pounds. So let's start with the solid geometry here. Go into components. We can easily switch between units in ANSYS, so this is very useful. I can do, I'm sorry, so we are going to go into the, we are using the global coordinate system here, so this has to be -10. So that's how I wanted it. So that's the force in this direction on this face. We can now repeat that for the shell and beam. Can group this into a separate folder. Okay, so the next step is to solve this. Let me just check if I have everything ready to go. Okay, so before we solve it, I need to change a few settings here. I usually turn this on by default, and since we are dealing with beams, we want to see the results, so turn this on. And let's see, deformation total, that's what we want. So with that, I can start my solution. Okay, so here's the result. This is the total deformation of the structure. So these two models are very similar, and the beam one is not. So let me go into it. So if I pick this edge here, the deformation is about 0.12271 inches, or I can just convert this into millimeters. So it's about 3 millimeters here, and yeah, so 3 plus millimeters here. But at this point, it's about 15 or 16 millimeters. Um, so the reason for this is, let me just go into the mesh here. Typically, when we fabricate these structures, these will be connected. Most likely, this type of structure is going to be welded, so the connection is going to be, there's going to be welds here, and we are not modeling the welds, but we are doing something close to that, which is, bonding this edge to the plate. So it's a very rough, you know, model of a welded connection. It's not exactly a weld. Uh, we are doing the same thing here. So this entire edge with all its nodes is merged into the plate. So that's where it is connected. But if you come down here on the beam model, we have this node, a single node connected to a single node, which is not exactly uh, the uh, the connection here. So, I want you to be aware of this type of modeling where, you know, we rush into creating a mesh with conformal type of mesh and ignore the connections. So I, you know, in another video, I can show you how to remedy this situation on the beam model so we can get identical results. But just to keep it simple, you know, we can suppress the plates for now. So I can pick the plates here, and to keep it, make it even simpler, I can suppress these members also. So right click, suppress. Okay, so these are suppressed, but we have lost our um, we have lost our fixed support. So I can redefine these. So I can do geometry here and come into this area, pick this face. So I'm just making this model simple for now. I'm removing the part which is causing the problem, and the idea is to make it work. So whenever we run into, any complexity, we can um, do a simpler analysis first, simplify the model or the geometry or loading conditions, and reevaluate it and see if we are getting consistent results. This one here is just a node. Okay, so after I've removed the plates and the diagonal braces, I can reevaluate this model. Okay, so now we can look at the results, and this time it looks like we are getting consistent results. So let me exaggerate this deformation here. I can probe the edge at this location and this node here. So as you can see, now we are getting consistent results in all these models. We can increase the resolution here. Let me just do this. Okay, so now we can bring in the normal stress, and instead of the global coordinate system, we can now select solution coordinate system. So now we can compare the normal stress, which is along the axis of these members. So x-axis is here in this member, and it's in this direction here. So we are getting consistent results. So this was the idea behind using these element orientations. So we can look at normal stresses in the correct orientation and compare the results. In this region also. Okay, so these models compare really well. I can then, just to validate my analysis, I can look at the reaction forces here. So these three, first of all, I need to put them into a separate group. So reactions. Okay, so the force reaction. So we were applying a force of 10 pounds in this direction. Let me just switch back to inch pounds, and as you can see, the the Z reaction is in the opposite direction, as we should be getting it of 10 pounds. Same is true for the shell model and the beam model. We can then just to check the moment balance, we can bring in the moment reaction, fix support 1, duplicate this, okay, so this can be renamed as force reactions, and I'm going to pick these three and call it moment reactions. Evaluate. Okay, so here's the result. So the x moment, which is, so all of this is in the global coordinate system. So the x-axis moment, which is, you know, the moment along this axis of this member. To help explain this better, let me turn the scale back. So it's along this axis here. We have a 2 by 2 inch cross section, square cross section here. So the distance from the center of this beam to the center of this beam, um, this is the center of this beam is where the force is applied, right? So the axis of, or the yeah, so the axis of the force is the center of the top beam, and the reaction is going to be along the axis of this beam. So this distance is 2 inches. So this is a 2 by 2 inch cross section. So the distance between from here to here is 2 inches between the axes of these two beams, and the force is 10 pounds. So 2 into 10 is 20 inch pounds, and that's what I'm getting for as my x-axis moment reaction. Same is true for the shell model. It's showing me a little a value which is not close to 20, but that's okay, you know, within the numerical accuracy of FEA. But it has more to do with the with the deformation of the structure as it's being loaded. So the direction of force changes. I mean, just keep in mind we are using large deformation option. The the y component, which is the largest component, which is along this coordinate direction, this axis here in the global coordinate system, uh, we can evaluate that as well. So this is, let's see how big this is. So this beam is about 49 inches long, and actually the point of application of the force is 1 inch less than 49, so it's 48 inches. So that's where the force is being applied. So the beam is 49 inches long, but the exact location where the force is being applied perpendicular to this beam is at a location of 48 inches from the end of the beam. So it's going to be 10 times 48, which is close to 480. So that's what I'm getting, 480 inch pound on the shell model. Very close to 480 in the solid model, and I'm getting the same result in the beam model. So here I have three models of different fidelity, and they're all showing the same results. Um, Ideally, I would model a structure like this using the shell elements, but the beam structure also works. If this is a very big structure, then I will switch over to the beam model. If it's a small structure like we have here, I think the solid model is going to suffice. The solution time is not is less than a minute. So in the next video, I'm going to show you how we can rectify this issue here with the plates. So if we unsuppress all bodies, so the issue with correctly modeling a beam to plate connection. So this is going to be the subject of my next video. Thank you.